Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today is our 21st lecture of Discrete Structures CSC 102. In the previous lecture we have discussed functions and sum and difference of two functions, equality of two functions. We have also discussed one-to-one, on-to and bijective functions. Today we are going to discuss inverse functions, how to find an inverse of a function, then composition of functions defined on finite and infinite sets, and then at the end we shall discuss how to find domain and range and how to plot simple functions. So what is the inverse of a function? As you know, the definition of function, what is the function, we have discussed in the previous lecture. The inverse of a function is basically if we have a function f from x to y which must be bijective function. So to find an inverse of a function, the function must be bijective, means it should be one-to-one and on-to, then we can find its inverse. Otherwise we cannot find the inverse of the function which is not bijective function. So inverse of a function is from, as by name we can, if this is a function f from x to y, then f inverse must be from y to x. This is reversed. This sets the domain of the given function becomes codomain and codomain becomes domain. So here you can see f must be one-to-one and on-to, that is as f must be bijective function. So then we denote f inverse like this, f inverse f power minus 1, we read it as f inverse from y to x, and we defined it as follows: f inverse of y, y basically is an element of capital Y. So that unique element x, f inverse of y, is equal to basically x. That x must be unique in x such that f of x equals y, that is f inverse of y, you can say it like this: f inverse of y is equal to x if and only if y is equal to f of x. Means this is from the definition of function f from f x to y, f from x to y. The function f power minus 1 or f inverse is called the inverse of a function. In this case basically x is the domain of f and y is the codomain of f. In this case this is f, and f inverse is basically in from this set to this set. For example, here we are given an arrow diagram of a function where x is the domain, y is the range, y is the codomain. You can see that this function is both one-to-one and on-to, as each element of x is connected to exactly one element of y, and all the elements of y are images of exactly one element in x. Therefore this function is basically one-to-one and on-to. So we can find the inverse of this function. I remind here, if the given function is not bijective function one-to-one and on-to, then we cannot find the inverse of that function. So we can draw arrow diagram of the inverse of a function in two ways. For example, first we write x first, here x, and then y, and we draw here f inverse elements of x a, b, c, d and e, and elements of y s, t, u, v, w. Now a image of a is v, so the inverse image of v is a. Image of b is s, inverse image of s is b. Image of c is u, the inverse image of u is c. Image of d is w, and inverse image of w is d, and e, inverse image of t is e. So this is how we can draw an arrow diagram of the inverse of function. There is another way. First we write the elements of y, or y set y, and then the set x, and we plot it, or we draw it like this, y to x. Now we write the elements of y, s, t, u, v, w, here a, b, c, d, e. Now s, image of s is b, image of t is e, image of u is c, image of v is a, image of w is what? D. So this is another way how we can draw an arrow diagram of the inverse of a function. So next is how to find inverse of a function which is defined on the infinite sets. For example, if we are given a function f from R to R, where R is the set of real numbers and is defined by the formula this: f of x is equal to 4x minus 1 for all real numbers x. Now this function must be one-to-one and onto. How to prove it? I hope you can prove it. In the previous lecture we have proved some functions which were defined on the infinite sets. We have proved them one-to-one. So this is an exercise for you to prove it one-to-one and onto function. Prove it one-to-one and onto. So now this function, I suppose you have proved it, and this function is now bijective function, or this function is one-to-one and onto function. Now how to find the inverse of this function? For any particular but arbitrarily chosen y in R, by definition of f inverse, basically f inverse of y is equal to x, such that f of x is equal to y. So f of x is equal to y, where f of x is equal to 4x minus 1, or we can write it as 4x minus 1 is equal to y. Now here we've tried to find the value of x. Means we try to find, or we try to separate the x, and we try to find an expression in which x is separate and y is separate. Means we try to find x as a function of y. Now here how we can proceed here: 4x minus 1 is equal to y. 1, we add 1 on both sides, plus 1. 4x minus 1 plus 1 and y plus 1. 1 cancels here. We obtain x. 4x is equal to y plus 1. Now we divide 4 on both sides. Here 4 can be cancelled, and x is equal to y plus 1 divided by 4. Now we have found an expression in which x is separate and x is basically the function of y. This is basically the inverse of the given function, and we denote it like this: f inverse of y is equal to y plus 1 divided by 4. So whatever the function is given, how we find the inverse? Whatever the function here is given, for example, there must be 5x plus 9. If this is a function f of x, then we write it as y is equal to 5x plus 9, and then we try to find the value of x, or we try to separate the x, and on the right hand side we find an expression for y which involves only y. And then we say that f inverse is basically here, f inverse of y can be y minus 9 divided by 5 y minus 9 divided by 5. So this is the inverse of this function. So this is how we can find the inverse of a bijective function. Now we have a theorem: if given function f from x to y, where x and y are any two sets which must be non-empty, if this function is both 1 to 1 and onto, then inverse of this function from y to x is also 1 to 1 and onto. Means the inverse of a function, the inverse of a bijective function is also bijective. Now here f inverse is 1 to 1. We have to prove that f inverse is 1 to 1 and onto. First we prove f inverse is 1 to 1. Suppose we are given y1 and y2 are any two elements of y, any two arbitrary elements of y, such that f inverse of y1 is equal to f inverse of y2. So this is the same procedure which we followed in the previous lecture to prove a function to be 1 1 or not. So we suppose that f inverse of y1 is equal to f inverse of y2, and we will try to prove that here we suppose f inverse of y1 is equal to f inverse of y2, and we shall try to prove that y1 is equal to y2. We shall try to prove that y1 is equal to y2. So this by the definition of a one-to-one function. Now if f inverse of y1 exists, then it must be equal to some element in x. So we suppose that x is equal to f inverse of y1, because both of these are equal, so f inverse of y2 is also equal to x. Then x must belongs to x, and by the definition of f inverse, f of x is equal to y1 and f of x is equal to y2, because x is equal to f inverse of y1. This is, we have written this by the definition of inverse function, as you can see here. F inverse of y is equal to x if and only if y is equal to f of x. Here you can see that f of x are both same. If we have two equations, these two equations, if the left hand sides of these two equations is identical, then the right hand sides must be identical. So consequently we can write y1 is equal to y2. So we have proved here this, that if we suppose this, then we can prove this. So therefore this function is 1 to 1 function. Similarly we can prove f inverse is onto. You can see it, I think it's obvious. So If a given function is 1 to 1 and onto, then its inverse must be 1 to 1 and onto. Now we shall discuss the composition of two functions. So if we are given two functions, f from x to y dash and g from y to z, be any two functions with the property that the range of f is a subset of the domain of g. So this is necessary here, that the range of f must be subset of the domain of g, means this set must be subset of this, means y dash must be subset of y. It may be proper or improper subset, therefore we have written here the improper subset. So y dash must be subset of y. We define then a new function, g composition f or g circle f. There are many different ways we can read it. G circle f, g composition f. So this function is basically from x to z as follows. How we define this function? G circle f or g composition f of x is equal to g of f of x for all x belongs to x. This is how we define this function. We shall discuss it in detail with the help of examples, where g circle f is read as g circle f and g of f of x is read as g of f of x. The function g circle f is called the composition of f and g. This is basically, here you can see that first we apply f on x and then we apply g on f of x. This is here f first we apply on x and then g we apply on this whole quantity, whatever it is, f of x. So this is called the composition of f and g. So in graphic, we can see it with the help of a diagram which is given by here. F is basically the function from x to y and g is from y to z. F is from x to y dash. Basically y dash is the subset of, this is y dash is the subset of y. F is from x to y dash and g is from y to z. Then the composition g circle f is basically from x to z. We can write it as g of f of x or g circle f of x. So now we see this is an example. This will help you to understand what is basically the composition of two functions. Let x is any set which contains 1, 2, 3. Y dash, this is basically y dash. Y dash is the set which contains a, b, c, d, and y is a, b, c, d, e. Now we can see here that y dash is subset of y, and z is the set which contains x, y, z, these three elements. Now we define function f from x to y dash and g from y to z by the arrow diagrams. You can see here x, f basically maps or relates 1 to c, 2 to b, and 3 to a. Here in the first function, d and e are not utilized. Basically f connects 1 with C, 2 with B, and 3 with A. So there are extra elements D and E of Y. Now G is defined from Y to Z. The image of A is Y, image of B is Y, image of C is Z, image of D is Z, image of E is Z. Now what is the composition of these two functions? How we can define the composition? This is in the composition, basically G circle f of 1 is what? G circle f of 1 is G of f of 1. Now we see that what is f of 1? F of 1 means what is the image of 1 under f? Image of 1 under f is C. So f of 1 is basically C. So we put here C. Now here in the second function we see what is G of C, means C is connected to here, C is connected to Z. So G of C becomes Z. So you can see here that 1 is connected to C and C is connected to Z. So therefore the composition of these two functions, G circle f of 1 is Z. Similarly, we now see 2 for the second element of X. 2 is connected to B, means f of 2 is B. Now G circle f of 2 is G of f of 2. Now 2 is connected to B, so therefore f of 2 is B. Now we see here what is the image of B? B is connected to Y, so G of B is Y. Similarly, G circle f of 3 is G of f of 3, and f of 3 has image A, and A is connected to Y, so G of A is Y. So the composition of two functions can be defined like this. If we draw an arrow diagram directly from X to Z of the composition of G and F, it will be like this. Here X is 1, 2, 3, Z is X, Y, Z. With the help of these expressions which we have calculated in the previous slide, G circle f of 1 is basically what is Z. So 1 is connected to Z, so 1 is connected to here Z. Here 2 is connected to Y, so 2 is connected to Y, and 3 is connected to Y again, so 3 is connected to Y. So this is how we can draw an arrow diagram of the composition of any two functions directly from X to Z. Now here the domain of this G circle f is X, and the codomain is Z, X, Y, Z, and the range is all those elements which are images of some elements of X. Then the range of G circle f is Y, Z, which is obviously the subset of codomain. Now how we define the composition of two functions on infinite sets? Let we have two functions, f from Z to Z and G from Z to Z. So these two functions have same domain, codomain, so there is no problem here. This set must be the subset of this set, means range of or codomain of f must be the subset of the domain of the second function. So this is Z is subset of Z, so this property is satisfied. Now we can define the composition of these two functions. The first function is defined by f of n is equal to n plus 1, and the second function is defined by g of n is equal to n square. We have to find the composition of these two functions, g circle f and f circle g, and then we have to investigate whether g circle f is equal to f circle g or not. The functions are defined as follows. Basically g circle f of n is basically what? G of f of n. Now what is f of n? f of n is n plus 1. So in place of f of n we write n plus 1. Now g of n plus 1 is what? Basically f is a function like this, f of n. Now f is a function like this, f of n is equal to n plus 1. How it is defined? When f operates on the elements of the domain n, it adds 1 in these elements. F of n, we add 1 in this element, and this is basically this is how this function is defined. And g is basically n is equal to n square. How g is defined? G, when g operates on the elements of the domain, it takes the square of the elements of the domain. Now here, what is the domain element of g? This is basically n plus 1. So how we have defined g, it takes the square of whatever we have defined here. Whatever we have defined here, g of n is basically n square. Now when g operates on this element, for example if we say it y or m, then what will be g of m? It will be m square. So m is n plus 1, so we must have n plus 1 whole square. So this is basically g circle f. Now we define f circle g. Now first we operate g on n. Here we have operated f on n first. Here we must operate g on n first. So this becomes f of g of n. So what is g of n? This is basically n square. Now when f operates on this element, for example this is m, this will become m plus 1. So what is m? M is n square. So instead of m we write here n square. So this is basically f circle g. Now whether this function and this function are both equal or not, in the second part we have to answer this question. It is evident if you see the functions. Here we have n plus 1 whole square, here we have n square plus 1. So these two functions are not equal. Obviously we can give a counter example to disprove it. For example, if we take 1 here, any element of the domain 1, and g circle f of 1 is basically what? 1 plus 1 whole square, which is 4. Now f circle g is basically 1 square plus 1, which is 2. Now 2 is not equal to 4. So therefore composition of two functions, g circle f and f circle g, is not necessarily equal always. So the next is how we define the composition of any function with the identity function. Let x is defined as let x be a set which contains a, b, c, d, y, u, v, w, and suppose f from x to y is given by the arrow diagram. F is given, this function f is defined by this, where x is a, b, c, d and y is u, v, w. So we can see the relation, the function, the relation between the elements of x and y, like they are defined by the arrows. A is connected to, A is related to u, b is related to v, c is related to v, and d is related to u. Now we have to find the composition of this function with the identity function. In the previous lecture we have discussed what is the identity function. You know it. Now we have to find f circle I x, I y circle f. Now here x is basically, first we define I f circle ix. In this case first we we operate this function ix and then f on the elements of ix. So ix is basically, we write x, you know, a b c, a b c d, a b c d. A is related to A, B is related to B, C is related to C, D is related to D. So this is what the definition of identity function. Now then we define f on the range of, on the codomain of basically range of I of x. Now A is related to U, the same what we have defined here. A is related to U, B is related to V, C is related to V, and D is related to U. So this is basically the composition of ix with f. You can see f circle ix of A is basically f ix of A, ix of A is basically A, so f of A is U. This is how we can find all the elements of the, all the images of the composition of f circle ix. So if we note here that f circle ix is basically is equal to f of x. Here f circle ix of x is equal to f of x, means the images of this function are equal to the images of this function. Similarly, we can verify here that iy circle f of x is equal to f of x by, you can now understand here the identity function is basically, this operates on the f of x, therefore we define it on the y set from y to y ix element. The image of u is u, image of v is v, w is w. So the composition of any function with the identity function, basically it is defined like this, and always f circle ix of x is basically f of x, and similarly iy circle f of x is also f of x. Means we conclude here that f circle ix is equal to iy circle f is equal to f. Means identity function, if we defined the composition of any function with the identity function, it changes nothing. We will obtain the same function which is defined here. So next is the composition of function with its inverse function. For example, if we are given a function this and its inverse is this, you can define it easily, as we have discussed in the earlier slides how to find the inverse of a function. Now we want to find the composition of function f and its inverse. That is, we have to find f circle f inverse or f inverse circle f. Here I have defined f inverse circle f. F inverse circle f, we operate on each element of x here, because first we operate f on the element. So this is f inverse of f of a. F of a is what? F of a is z, so f inverse of z. Now what is f inverse of z? This is a, we get a. Similarly, f inverse circle f of b is what? F inverse of f of b. Now what is f of b? F of b is x here. Now f inverse of x, f inverse of x, x is connected to b, so this again comes to b. F inverse circle f of c is basically f inverse of f of c. C is connected to y. Now y is connected to c, so f inverse of y is c. Here we can see that the image of A under the composition of these two functions. Image of A is A, image of B is B, image of C is C. So this is basically the property of basically you can see here F inverse circle F, how we define it from the first set X to the second set X here, because the composition of F inverse and F is from X to X. This is A, B, C, this is A, B, C. Using these relations we can see that this is A is related to A, B is related to B, B is related to B, C is related to B, C. So this is basically the property of identity function, because the image of A is A, image of B is B, image of C is C. This is basically the property of identity function. Therefore we can say that F inverse circle F is IX. Means if we take the composition of a function with its inverse, then it will give us the identity function. Similarly, we can show that, we can prove that F circle F inverse is also IY. Similarly, we can show that F circle F inverse is equal to IY. Means again we obtain that the composition of F inverse and F is IY. So we conclude here that composition of a function with its inverse gives us the identity function. Next is a composition of one-to-one functions. How we define the composition of one-to-one functions? If we are given any two functions which are one-to-one, for example here F is from X to Y and G is from Y to Z. Both of these two functions are one-to-one. You can see in the arrow diagram. Now composition of G and F, G circle F is basically defined from X to Z. Now here we have A, B, C. In Z we have 1, 2, 3, 4, 5. You can see here that image of A is W and W is connected to 1 under the G. So A is connected to 1, B is connected to Y, and Y is connected to 4. So B is connected to 4. C is connected to Z and Z is connected to 5. So this is connected to 5. So G circle F, you can see here that this function is also one-to-one function. So we conclude here that if we have two functions F and G which are both one-to-one function, then their composition must also be a one-to-one function. Similarly, we can see whether a composition of two onto functions is also an onto function. Next we try here to find how to find the domain and range of the infinite functions, because in the previous slides, in the previous lectures of functions, we can easily find the domain and range of the finite functions, of the functions which are defined on finite sets, but we haven't discussed how to find the domain and range of the functions which are defined on infinite sets. And then we shall try to we shall discuss how to plot, how to draw the functions which are defined on infinite sets, because the functions which are defined on finite sets, we can draw the arrow diagram here like this, but if the functions are defined on infinite sets, then how we can plot those functions. For that we need basically infinite functions are usually defined on the set of real numbers. So we discuss here how to find the domain and range of the functions which are defined on the set of real numbers or any subset of the real numbers. For that you need to know how to define the intervals on the real line. Basically you know what is real line. So this is a real line, you know it. This is from minus infinity to plus infinity, from 1, 2, 3 and so on, 1, 2, 3 and so on. Here we have negative integers, right, negative numbers, minus 1, minus 2, minus 3 and so on up to minus infinity. On this real line we define the intervals. The first is basically the finite intervals and infinite intervals. The interval AB with the small brackets which are called parentheses, or we say these brackets small brackets with AB. This is basically an interval on the real line which contains all the elements between A and B but not the A and B. We draw it on the real line like this with the circle here, which shows that A is not included in this interval, B is not also included in this interval. If the circle here is open, means it's not filled. If we have interval defined like this with the capital brackets AB, this interval is basically closed interval and the previous interval is basically open interval because the endpoints of the intervals are not included in these set of numbers, real numbers. But this interval is basically called closed interval, and this contains also the endpoints because the circle is filled. We have semi-open or half-open intervals in which here we have capital bracket, here on this side we have small bracket between any two numbers AB, maybe any real numbers. So in this case we have B is open because B is not included in this interval and A is included in this interval. Similarly, A here is not included, B is included. So this is how we can define finite intervals. Now infinite intervals. Open interval A infinity means infinity is not included, A is not included, so A with a circle and goes up to plus infinity. In this interval A is included but infinity is not included, so circle is filled here. This is minus infinity to B, this is minus infinity to B included, this is minus infinity to plus infinity. This is basically the set of real numbers itself. So this is how we can define the intervals on the real line. Now how we plot the functions which are defined on infinite sets, especially on the set of real numbers. The functions are, we plot them on the Cartesian plane. This plane is basically called Cartesian plane. This is called x-axis, this is called y-axis. Here we define 0, which is basically called the origin. This is called positive x-axis, this is negative x-axis, positive y-axis, negative y-axis. Positive numbers, positive x-axis basically contains positive real numbers. Here we have positive, here we have negative, and here we have negative y numbers. This Cartesian coordinates basically in the plane are based on two perpendicular axes intersecting at the origin. Then how we plot function. For example, if we are given a function y is equal to x plus 1, this is basically the equation of straight line you have studied in earlier classes. So plotting straight lines is basically very easy in the Cartesian plane. We take any 2 points, for example x we take 1 and y we take 5. Here we have taken 3 and 4, so first point you take here 3 and 4, because if we take x as 3 then y must be 4, and the other point we choose here x minus 2 and y must be minus 1. If we take point 1, this is A, this is the point B. On the Cartesian plane we plot this point 3 4. Here we have 3, here we have 4, so this is this point. The second is minus 2 minus 1, this is minus 2 and this is minus 1, so this point come here. So we join these 2 points by a line which shows the graph of this straight line. Straight lines are very easy to plot on the Cartesian planes. Sorry. The next is how to plot a function which, for example, this y is equal to x square. The next is we try to plot a function y is equal to x square. This function y is equal to f of x, where f is defined from R to R, the set of real numbers. This function, how we plot, we choose some arbitrary values of x and y as you do in the early classes. You choose any arbitrary values of x just to mark the points on the Cartesian plane. We choose 0, we choose x 0, 1, 3 by 2 and 2, any. So if x is 0 then y is 0 square is 0. Here 1 square is 1, 3 by 2 square is 9 by 4, 2 is 4. So we have obtained 4 points, 0 0, 1 1, 3 by 2, 9 by 4 and 2 4. On the Cartesian plane we plot these 4 points. For example, the first point is x0 y0 is here, then x1 y1 is here, x is 3 by 2, y is 9 by 4, it will come here, 2 4 come here. Here we have a square function. If we choose 1 it will give 1, if we choose minus 1 it will again give 1, plus minus, here we choose, here we get obtain plus 1, plus 9 by 4. If we choose here plus minus 2, here we get 4. So choose some positive and some negative values of the x and then find the values of y. We have minus 1 1, minus 3 by 2, 9 by 4 and minus 2 4. Again these 4 points, this point and this will come here. This point is basically minus 3 by 2, 9 by 4. So we draw some points in the Cartesian plane and then join these points. So this is basically we obtained the graph of this function y is equal to x square. So similarly, I repeat here, to plot any function which is defined on the real lines, just take some arbitrary positive values of x and negative values of x. arbitrary. Then find the values of y. You will obtain the points like this. Then just mark these points or draw these points on the Cartesian planes, and then join these points. You will obtain the graph of the function. Now how we find the domain and range of any given function, which are defined on infinite set, particularly on the set of real numbers. For example, if we have the function y is equal to x square, which we have, for example, the first function is defined by y is equal to x square, which we have plotted in the previous slide here. Now the domain is basically, domain shows, or we plot the domain on the x-axis, and the range is basically plotted on the y-axis. Domain is basically all possible values of x which can be taken here on the x-axis, and the range is basically all possible values of y which we can take on the y-axis. Here you can see that we can take any value of x. Here we will obtain some value of y here. So the domain here could be minus infinity to plus infinity open interval, because minus infinity and plus infinity are not included. So domain could be any number on the real line. So the domain is basically, if we denote it by d, so this could be minus infinity to plus infinity. Now range is basically, as the graph we have plotted, it is only on above x-axis. Therefore the range contains only the positive numbers plus 0, because 0 comes on the plot, and this plot goes up to what? This plot goes up to plus infinity. So the range is basically here, the domain is minus infinity to plus infinity, and the range is, if we denote it by r, then range is 0 to infinity open interval, because in this function whatever we put the value of x, the y is either 0 or a positive number. Y cannot be negative because here we have square. So this is how we can find the domain and range of a function. There are some things which we must be careful about. That, for example, in this function y is equal to 1 over x. For example, in the second function y is equal to 1 over x, here x cannot be 0, because you know that 1 over 0 is infinity. 1 over 0 is infinity. So we cannot take the values of x equal to 0 here in the denominator. Any other value of x can be chosen here. It will give us the value of y, but we cannot choose here the value of x as 0. So the domain of this function must not contain x equal to 0. So the domain could be minus infinity to 0 union 0 to infinity. We have excluded 0 from the set of real numbers, because if we define 0 here, if we put 0 here, we will obtain infinity undefined. So this function cannot have x equal to 0. Similarly, if we have some other function y is equal to 1 over x minus 1, x minus 2, so the domain of this function, what will be the domain of this function? If we define x is equal to 1, this function goes to infinity. If we define x is equal to 2, this function becomes also infinity. So the domain of this function must not contain 1 and 2. So how we can write the domain of this function is like this: could be minus infinity to 1 union 1 to 2 union 2 to infinity, because we have to exclude 1 and 2 also. So from the real line we have excluded 1 and 2, so all other values of x are possible here except 1 and 2. On the real line, how we can plot it from this to 1 to 2, and this minus infinity to 1 1 to 2 2 to infinity. This is how we can show the domain of this function on the real line, because here we have not filled this circle. It means 1 is not included on the real line, 2 is not included on the real line. So the domain of functions like this, which are basically the rational functions, we must exclude those values of x on which the function becomes infinity or undefined. So this is basically the first thing we have to care about in defining the domain of the functions. The second thing here, for example, if we take this function under root square root of x, for example here we define y is equal to square root of x. Now in the square root functions, the variable must be greater than or equal to 0. Whatever we define in the square root of any number, or we can you can say that square root of negative numbers, for example -2 -5, this is not defined on the real line. So when we have any square root function, for example y is equal to x minus 2, this whole quantity must be greater than or equal to 0. The expression under the square root must be greater than or equal to 0, because in the square root function the negative numbers are not defined on real lines. So to find the domain of the functions which involve square root, the expression in the square root must be greater than or equal to 0. For example here, for this function, domain is what? Domain is any number which is greater than or equal to 0, means this is domain of this function is 0 to infinity. Now for this function, what is the domain? Domain is basically y is equal to x minus, sorry, the function is this, the domain must be, this must be greater than or equal to 2, means x is greater than or equal to 2, means all those values of x which are greater than or equal to 2 we can put here. Therefore the domain of this function must be 2 to infinity, 2 is included and infinity is excluded. So the domain and range of the functions which involve square root we can find like this. Domain is, so the range of this function is, if we put 0 here we get 0, and if we put the larger numbers we get the larger numbers. So the range of this function is basically this, and the range of the function which we have defined here could be, if we put 2 here we get 0, and if we put the numbers which are greater than or equal to 2 we get the larger numbers. Therefore the range of this function is basically from 0 to infinity. So range is basically all possible values which we obtain by inserting the values of x. So if we put here 2 we get 0, if we put 3 we get some number which is greater than 0, and similarly by inserting larger numbers we get the larger numbers up to infinity. So the range of this function is 0 to infinity. Similarly you can see the domain of this function, how to find the domain of this function 4 minus square root of 4 minus x. Square root of 4 y is equal to square root of 4 minus x. Now 4 minus x, now 4 minus x must be greater than or equal to 0, because in the square root we must have always a positive number, positive real number. So means x is less than or equal to 4, and x cannot yes, x is less than or equal to 4. All possible values of x which are less than or equal to 4 we can put it here. So the domain of this function is basically what? Minus infinity to 4, and 4 is included, infinity is not included. Similarly, we can find the range of this function which is given here. If we put 4 here, the domain is minus infinity to 4. If we put 4 here, we get 0, and if we put the numbers less than 4 up to minus infinity, we get larger numbers. So the range is this. Similarly, we can find the domain and range of this function. So this is how we can find the domain and range of any function which is defined on the set of real numbers, and we can also plot that function. Another example of the function which is the absolute function, you can see y is equal to absolute of x. We have defined it in the previous lectures. This is basically x minus x when x is greater than or equal to 0, when x is less than 0. So we can plot it on the same manner. We can find the domain and range of this function. Similarly, a floor function which we have studied in the previous lectures, this is basically floor function. We can plot it like this. You can see the graph of the floor function on any book of discrete mathematics, and or you can find the graph of this function in any book of calculus also. Similarly, we can plot the ceiling function also. So for today it is I think it is enough. We stop here, and today we have discussed the inverse of a function, how to find inverse of finite and of functions which are defined on finite sets and infinite sets. We have discussed the composition of functions, composition of a function with identity function, composition of function with its inverse, and then we have briefly discussed how to find the domain and range of a function and how to plot a function on the Cartesian plane. In the next lecture we shall start sequences and series or summation. Until the next lecture, Allah Hafiz.